Okay, good morning, good afternoon, everybody. So, actually, this is lecture 16. This is continuation of your lecture 15. Just a second. Okay, so last class we discussed depth first search. We still have to do breadth first search, but before we move ahead, we will discuss something related to depth first search. So, uh, this is okay. So we did depth first search on graphs and we were discussing the runtime. So if you look at the algo here in this slide, the work done for every vertex, you are checking the adjacent vertices or the edges, and you whenever you find that an adjacent vertex is gray or black, you do not uh, consider that to for traversal. That means that something that has been already touched or traversed, you will not go there. So for every vertex you will check all the adjacent vertices and all the adjacent vertices of a vertex, and this will be only in one direction. So in the sense that if you are going from u to v, you will not, when you go to v, you will not be checking u, because that's going in the backward direction unless you are returning back. So for every adjacent vertex you see in this, let me just mark it here, you see that the runtime is for every edge of a vertex, every adjacent edge. So overall you'll explore e edges, and here whatever work you're doing, you are calling firstly you're mark coloring everything white, then you're calling dfs for all the vertices, and for every dfs you're checking all the adjacent vertices. So it is v plus e and not v into e, because you do not explore v times the number of edges, you are exploring all the vertices and all the edges. Okay, so that's your dfs. Now this concept of, let me see if I have to admit some more students. Okay, so there's something known as topological sort. So this concept is applicable on graphs that are directed and they are acyclic. We call them DAG, directed acyclic graphs. So it is a kind of sorting of the vertices, and how we perform this sort, that is by performing a depth first search on the graph. So we know that depth first search will visit all the vertices in the graph and in order, and the sorting of the vertices is in the order in which we visit them. So how we do that, we we traverse starting with a given source node to, obviously you form a dfs tree. At the end of a depth first search we form a dfs tree, and that dfs tree is not something which you can call sorted. So what we do, we linearly arrange all these vertices. Instead of having a depth first search tree, we kind of present them in the form of a linked list. So we'll see with an example how we, it's the same dfs tree but it's in the form of a linked list. Just a second. Okay, so let this be an example graph. on which we have to perform a topological sort. Okay, not a depth first search, topological sort. So we will start here. Okay, from A, just performing a uh, just performing a depth first search. You start at A and you check its adjacent vertices. So let's pick them up in. Okay, this is not a directed acyclic graph. So let's first do it on this and then we'll do it on something else. So what you start at A, you go to the first adjacent vertex B. So marking it with a circle is marking it with gray. Then you go, let's say, to E. So this is gray. You go back to F. Then you go to D. So when you check the adjacent vertices of D, all are gray. So there's nothing. You more to no sorry, C is there. So you come here and C also becomes gray. All the adjacent vertices of C are gray. This circle mark is color gray. And now because it's gray, I have to return back. So C becomes black. So whatever you finish for topological sort, it's going to be a it's going to be a I'm getting people are in the waiting room, but I'm not able to see the waiting room. Aman, can you see anything?
Yes, ma'am.
There are people in the waiting room. Can you see it as but when I open the participants, I don't see any waiting room. Just a second. Normally I see people are waiting and I admit all. But then I am getting the message that yeah, yeah, I'm seeing that now.
Ma'am,
Yeah, yeah.
can
Okay.
see that.
Huh. Okay, fine, done. So okay, ये सब चला गया by stopping the share. So we were like going like this, and now we are returning back. So C becomes black. So you put C at the beginning of a linked list. As you finish exploring a vertex, which means as your vertex becomes black, you put that vertex in a queue. And every time you finish something, now next D becomes black. So you insert that at the beginning of the queue. So this is your start is this side is start and this side is end of queue. Then you go to F, then F comes at the beginning of the queue. Then when you return to E, then E will come here. Okay, I'll just take it here. Next after E, B, and then A. So this is the sorted order of the lists based on. So this time we had a single traversal. We'll see in one more example where you have a directed acyclic graph. Just a second. Okay, let's do one thing. I will make this graph directed and hopefully acyclic. I think I put the wrong graph. It had to be a directed acyclic graph. So I think I have marked all the edges with the direction, and it is not acyclic. One, there is one. Okay, there's only one cycle which I will remove. Okay, so now I think it becomes acyclic. We'll get to know if we face an error. So we start our topological sort by performing a DFS on this graph. So I start at A, and uh, A has three adjacent vertices. I will traverse this direction first, go to B. B has two adjacent vertices. I'll traverse here, go to E. From E, I can go to F. From F, there is no outgoing edge, so I am ending at F. That means this traversal ends at F. So I have to return back from F. So F becomes black, and I put F at the beginning of a linked list. The linked list currently is empty. So let me put it a bit on the right here so that I can draw on the same screen. So this is my linked list, and I put F in that. So from F, I come back to, let me use some other color. Okay, this is my back. So I back track. So from F, I backtrack to E. E again, there is no outgoing edge from E other than the one I already traversed. So E becomes black, and I insert it at the beginning of this linked list. So the linked list looks like this. Then from E, no outgoing edge. So I have come back here to B. B has an outgoing edge other than this one. So I will traverse from B to C, and C is also marked gray. This is my gray. And from C, one outgoing edge goes to F. F is already black, so I can't go there. So I can go to D. Okay. So now I'm at D, and D has an outgoing edge to F, but F is already black. So I will return from D. So D comes here. Okay, I insert D at the beginning of my linked list. From D, I come back to C. Again, everything is marked, so C will also be turning black, and I insert it at the beginning of the linked list. From C, I come back to B. Now B again, nowhere to go, so B also turns black. From B, I come back to A, which is my starting point, and now there's nothing more to explore. So A also turns black, and I insert it at the beginning of the linked list. So now you have the linked list in front of you. What you're supposed to do, you are supposed to add the edges of the existing graph to this linked list. So there is an edge from A to B. Let me put it in some other color. There's an edge from A to B with a weight of 6. There's an edge from A to C with a weight of 1. There's an edge from A to D with a weight of 5. Okay, so these are 3 edges. Now moving on to B. From B there are 2 edges, B to C with a weight of 5, and B to E, B to E. Okay, so B to E goes like this, and the weight is 3. Okay, done all the edges of B. Next you see C. C has 2 outgoing edges. One is C to D with a weight of 5, and C to F with a weight of 4. Okay, next is D. D has one outgoing edge to F, which has a weight of 2. Okay, there's no more outgoing edges from D. And then E. E has one outgoing edge to F, which I have already marked, and the weight is 6. And F has no outgoing edges. So this graph with these colored edges, this is the topological sort of this directed acyclic graph. If there is a cycle in this graph, then you will have some arrow like this going back if there is a cycle. That's why you cannot have a topological sort if the graph is cyclic. What we mean by sorting, we are able to put all the vertices in order, like on a straight line, with all the edges in the graph going from left to right. There is no edge that goes from right to left. So if you, even without doing DFS, if you're able to put all the vertices on a single line and then draw the edges and all the edges go from left to right, that will be a topological sort. So again, topological sort will, this order might change based on how you traverse. So I went from A to B to E first. You could have gone from A to B to uh, C to D. Okay, then the order would have changed, but all the edges would still move from left to right. So this is known as a topological sort of a graph. All you are doing is you are performing a depth first search. So depth first search takes V plus E, O of V plus E, and you are inserting in a linked list at the beginning of a linked list. So you're doing how many vertices you are inserting is V. So O of V plus O of V. That much extra time will take to sort a graph in this order. Why we do it? Because this kind of helps in finding the shortest path in a easy way. We'll see when we have uh, shortest path algorithms. What we did already was Dijkstra's algo. It does not deal with negative edges. There is another algo, Bellman-Ford, which deals with negative edges. Your DAGs will also work with negative edges once you have sorted them. Okay, so let's move on. So we'll again come back to this topological sort, how it helps us to get a better algo for single source shortest path. So shortest path has many applications. So when you have a map of cities, you want to calculate the flying times or even by road distance, distance between street corners, cost of doing any activity. Let's say I've been giving you the example of wiring. So you want to connect all the nodes uh, from a source point. How would you do it in the shortest possible way? So we have to keep in mind the costs or the weights of the edges that we draw in the graph, and based on that, we can find the shortest path. We have done single source shortest path Dijkstra's in the greedy algorithm part. So we'll be also doing Bellman-Ford. Bellman-Ford takes care of negative edges. You can't have negative edges in Dijkstra's. And then we also have the DAG shortest path algo, which helps us to find the shortest path from source to all the vertices using topological sort, which is basically essentially using DFS. Then you have algorithms for all pairs shortest path. So we are not only finding the shortest path from source to all other vertices, we are finding the shortest path between any two vertices that you are considering. So Floyd Walshall is one algo. It is done using dynamic programming, and there's one more, Johnson's. If we get time at the end of the course, if we are done early, which I think we will be doing these two. So for now, we'll be doing only Bellman, Ford, and DAG shortest path. So I think we went through this earlier as well. A shortest path from U to V will have other shortest paths in between. Uh, that's what Floyd Warshall algo uses. So if you're talking of the shortest distance from A to D and you have B, C in between, so you'll obviously be taking the shortest distance from B to C. Because if you don't do that, then your overall distance will not be the shortest from A to D. Okay. So given a directed graph with weighted edges, we have to find shortest paths from source to all other vertices. So if you notice, these algos say single source shortest path from source to all other vertices. So basically, since shortest paths of uh, between source and some particular vertex will include shortest path from source to any other vertex. So what they are trying to say essentially is that you cannot find the shortest path to only a single vertex in the graph, because eventually you will be calculating shortest path to all the other vertices, because the shortest path to a particular vertex will contain shortest path to some other vertex in the graph. So you have to keep in consideration all of those shortest paths before you can decide on the shortest path to a particular vertex. And again, like I said, we are not only finding the distance, we also want to find the path. So in Dijkstra's, we were just storing the key value to see what is the order, but we also store now the parent of, so that we can trace back what is the shortest path, what is the sequence of vertices in that. Okay, now moving on to Bellman-Ford algo. The first difference between Bellman-Ford and Dijkstra's is it handles negative edges, negative edge weights, and it also detects negative cycles, but it is slower than Dijkstra's. What is a negative cycle? You can have a cycle in the graph. Cycle would mean that you can go from A to B to C and then come back to A. Okay, this is a cycle because you can go and come back to the starting point. Okay, now since it allows, Bellman-Ford algo allows negative weights, there is a possibility of having a negative cycle. What do we mean by a negative cycle? Is that, for example, let me name these vertices A, B, and C. So I might ask you, what is the shortest distance from A to C? Shortest distance from, oh yes, A to B. So you'll say shortest distance from A to B is 5 plus minus 10, which is minus 5. Okay. Now, if I, so the path is A to C to B. This is the shortest distance from A to B. But if I take this path, basically I go around twice. So A to C is 5. This is minus 10. A to B to A is 4. Again, A to C is 5. And again, this is minus 10. So if you add this 10, you get 10 and 10. This cancels out. You get minus 6. So technically minus 6 is less than minus 5. So if I take one more, so initially I did this. Then second time I did this. Third time, if I do 1, 2, and 3 cycles, every time I will reduce my weight. Why? If you what is the cost of going around in this cycle? It is 5 plus minus 10 plus 4, which is minus 1. So every time you loop around, so if I make another loop, my whole path weight will reduce by minus 1. So every time, if I keep on going round and round, my smallest distance will always keep reducing by minus 1. That's why we call it a negative weight cycle. You can have, if for example, this was not minus 10, this was minus 3. Then going from A to C to B to A, the cycle cost is 6. It's a positive cycle, it's not a negative cycle. And if you try to take another loop in the same thing, you will add the distance. There'll be some positive addition to your distance. But in case when your cycle, this cycle weight is negative, then every time you loop around, if you make another round, you will get a reduced weight or a reduced length of the shortest path, which obviously in a way then your algo will never terminate, because every time you loop around you will find something which is less than the previous value. So we had minus 5 first, next time we'll have minus 6, next time we'll have minus 7. So we will keep on updating our shortest path, and the algo will basically not terminate, or even if it terminates, you'll always find a lowest short value for the shortest path. So if there is a negative weight cycle, Bellman-Ford algo will tell you that there is a negative weight cycle, and which would mean that you will possibly, if you want to do one loop around as many times, you will find the shortest path. So just a second. The way Bellman-Ford works, it will give you the shortest path from source to all other vertices, and it does it in an exhaustive way. And if after doing it in the exhaustive way, the Bellman-Ford algo can still find some shortest path distance updated, that means there is a negative weight cycle, and that this algo will inform you, and then you would know obviously that you'll not have a single shortest path. Okay, I just skip this algo. So what does let's skip the theory, let's look here. So what does Bellman-Ford algo do? So first of all, just like Dijkstra's, for every vertex it assigns a distance of the shortest path to infinity. The parent of the node is null, and the source node distance is set to 0, just like in Dijkstra's. Now, for every vertex, so there are v vertices in the graph. For every vertex, for every edge, so if there are 10 edges in the graph and there are 5 vertices only, this loop will run 50 times. So this is why I said that it does a exhaustive relax. So what is relax? I told you, if you have two vertices u and v, so there is some path coming, and the distance of this is du, and the weight of this edge is represented like this. So relax, what it does, if the distance of v is greater than distance of u plus weight of the edge u to v, which means that dv, v already had some distance associated with it, dv, maybe through some other path, through some other node. Okay, so there was some, let's say it was not infinity, it was some value that is stored there. Okay, then if you find that the distance, just a second, the distance of v plus the weight of the edge from u to v, if basically following this path here plus this here from u to v, if this distance is less than the existing distance for this particular vertex, then I will update my dv. So because that means I have found something which has a smaller weight or smaller cost. If if this is existing is greater than this new path which I have come to or I have reached, then I will update. This is basically what your relax function does. So you are doing it for all the edges. So you will see that it is exhaustive. Okay. And so basically till here I am exhausting, doing an exhausting relax on all the edges, and that updates all the vertices with the best distance possible. Now, for what I do after that, I'm checking once more. After doing an exhaustive search, I, for every edge UV belonging to the edges of the graph, if for any vertex you get that the distance of that vertex is greater than, that means you can still update it again, which means that there is going to be a, is a negative cycle in the graph, because when you're given a graph in a program you don't see the graph visually, so you won't be able to figure out if there is a negative cycle or not. So you will return a false, which would mean that there is no actual shortest path from source to all other vertices. Otherwise you return it true, and the runtime is clearly comes from this loop here. It is v into e. Rest is all something you can neglect because this takes the major chunk of your time. So let me see if there is a, okay, let me find an example to do. Just give me a second. Okay, if you have any questions till then, I'm just trying to find a relevant example. Okay, I have this example here, which is kind of done because it takes a lot of time to uh, actually do it on paper. I'll be sending you this. So you are starting from a source vertex. If you see, everything is initially if you see the stacks of these values, these are the values that get updated for the distance. So everything is here infinity first. Okay, and then you start your algo. Take a brighter color. You start your algo with source node as 0. So what does the algo do? It takes for first vertex, for example, and for all the edges, you are at vertex number 1. If you look at the algo says from the number of vertices 1 to n minus 1. You are, for every edge, you will relax. So what does relax mean? So if you're looking at the edge S to A here, how do you relax A? You see what is the distance of A? It is infinity. Is distance of S plus 5 less than infinity? Yes. So you update it to 5 here. So the same you do with C. 0 minus 2 makes it minus 2. Then take the next edge. What is the next edge? C to A. Minus 2 plus 2 makes it 0, right? Take the next edge, A to B. A to B is 1. So 0 plus 1, okay, is it's actually 1. But if you had, suppose you took the edge C to B first, then minus 2 plus 4 would be 2. Or if you came from C to D first, so the distance is minus 2 plus 4 is minus 2. It depends on the order they have taken. So uh, if you come to B via C, then it's 2. If you come via A, it is 1. So these are all the different iterations. If you come to D via B, it will eventually be 0, 1 minus if you're taking the best. So these are all the intermediate values that you see here. B to T is, if B was 6, 6 plus 3, you would get 9. If B was 2, 2 plus 3, you would get 5. Or if you take this here, D to T. So all these values will get updated. You have to do it in order. I don't know what order they followed here. So basically, in all the different rounds, you will get the best values for the distance. And because you're doing it extensively and exhaustively for all the edges, so there are 6 edges in this case, and 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9, sorry, 6 vertices and 9 edges. So the relax will run overall 54 times. So based on which vertex and which edge you're talking about. You're talking, if you're taking the edge SA, it will relax. Then next time again you will take SA. So how many times will you do that? You'll do that 6 times to see, maybe, or let's say I took AB edge first time. So B had some value based on the value of A. Once value of A changes, it will get reflected on value of B as well. So you have to do it exhaustively for uh, let me see if there is one more example I can give you. Okay, let's finish DAG and then we come to a, or let's do a whiteboard problem. I'll make a small graph myself. A, B, Okay, so let this be my graph, and let's mark the initial values of the distances. A is my source. So now you will take every edge in the first round. I'll have 6 rounds. So let's say in the first round, you have to take all the edges. Let me just write down all the edges. Sorry, it's not A to B. It is A to D, then B to A, C to B, C to D, C to E, E to F, and C to F. Okay, so in the first round, when you take each edge, so let's take in the order A to D. So 0 minus 1, F to C. Oh, I forgot one. Okay, C to F, wrong. Okay, to F to C. Okay, so let's take so A to D. Distance of A is 0, distance of D is infinity. Obviously, 0 taking this path from A to D, you are getting a distance of 0 minus 1. So this gets updated to minus 1. Now take B to A. B is infinity. Infinity plus 3 does not get a smaller value, so nothing gets updated. Then C to B. The again distance of C is infinity. Nothing gets updated. C to D. D is already minus 1. This is not getting updated. And so on. C to E, E to F, and F to C will not get updated because it's all infinity minus something. It doesn't make sense. Next round. Now, uh, again, you take A to D. A to D is 0 minus 1. Nothing changes. Uh, mhm. There's no more outgoing edge, so this will not, it will just stop there. This should be, let's change this to D to C. Just making this change. So this is D to C. Because this, there has to be an outgoing edge from the source. Otherwise, actually, there's no path. We were going from A to D, and that's it. There was no path to any other vertex. So we have just made that path now. So okay, so minus 1 plus 6 is 5. So C gets updated to 5. So 5 plus 3 is 8. So B gets updated to 8. 5 minus 1 is 4. And 5 minus 2 is 3. So this is round 1. Okay. Now round 2, again A to D, minus 1 stays. D to C, uh, maybe that's में कोई change ही नहीं होगा because I just drew the graph. D to C is again 5, and 5 3 is 8. Again nothing. So if you see FC, F has, yes, we forgot that. FC in the second round, when you see FC is minus 2. 3 minus 2 is 1. So this edge changes the distance of C to 1. Okay, in the third round, again A to D, nothing changes. D to C, D to C, obviously nothing changes. C is 1 now. So 1 plus 3, this will become 4. 1 minus 1, this will become 0. 1 actually, no, we did a mistake. I'm rubbing this off. We did a mistake here. First round में ही गलती की. Let's do it now. Okay. So this is 5. 5 minus 1 is 4. And this is not 5 minus 2 because you cannot come to F from C. You have to come from E. So 4 plus 4, this is 8. So next time when you update, 8 minus 2 will be 6. 5 is still less than that. I think इसमें तो और कोई change ही नहीं होगी उस graph में. Mm, I don't see any more updates happening because C has only 2 incoming and they are not giving a lesser value. So I think this pretty much the distances are going to be uh, the same because B has only one edge incoming, so or everybody has pretty much one incoming edge other than C. So कुछ और update नहीं होगा. The C's double edge will also give you a value of 6, so nothing will change. So I guess this was a very bad example because I just created it on the go. I'll give you one more example to practice. So let's get back to not this one. Let's get back to here. Okay. So this is again talking about negative cycle. So now we want to do the single source shortest path in a DAG. DAG is a directed acyclic graph. So what is the purpose of having a topological sort in this? Because then in case of Bellman-Ford, we are doing exhaustive, we are doing V cross E times relax. So here we can do relax in the order of vertices because we know if you go from left to right, the edges are coming from left to right. So if you have already edited the distance or found the So if you have found the distance of S, there's no back edge to S. So nothing will get updated after you have kind of crossed S. You have started walking from S to node number 1 to 4 to 6. You There's no back edge to S, so S will not get updated once again. So you'll see that here in the example. So how do you find shortest path? Sort it in the order as we discussed earlier. For every vertex taken in order. So you start from the leftmost vertex, do a relax. So all the incoming edges of S, you will do relax for that and then move to the next one. So here is an example of a graph which has been topologically sorted already, and this is the topological sort of the graph given to you. And what they have done, they have inside the nodes they have put the distance, so the edges are marked. You If you see, S is the source. In the topological sort, R is behind S. So when I am starting my single source shortest path, my source is S. It need not always be the leftmost vertex. So that means there's obviously, as you can see, there is no path from S to R. So obviously, when you're trying to find a shortest path from S to some other vertex, there has to be a path. If there is no path, there is no shortest distance at all, which means the distance is infinity. So what do we do in topological sort? Why we do it? Because we do some extra work in sorting, but it saves us the exhaustive relax we have to do in case of Bellman-Ford algo, which is expensive than your Dijkstra's algo as well. So topological sort means we have to take care of the vertices in the order prescribed. Just a second. So you start at R, the distance is infinity. There are no incoming edges to R. So if you say relax, relax R would mean you would relax it for all the incoming edges. So uh, if you see here, for every vertex taken in order, for each adjacent vertex in U, do relax. So adjacent vertex of R are all lying ahead of R. They are not lying behind R. So if you try to relax those edges, you have to do infinity plus 5 for S. So obviously that is not less than 0. Okay. Infinity plus 3, again it's infinity, so nothing will change for all there are only two adjacent vertices, R to S and R to T. It will not change the distances. So you did relax for all the edges related to R, you move on. Now we are at S. The distance is 0 for S. There are only two outgoing edges. So you will use distance of S plus the weight of the edge. In case of ST, it is 0 plus 2. In case of SU, it is 0 plus 6. And you have updated the distance for T and U. So now when I move ahead to T, I know S will not get updated any further. In fact, T will also not get updated any further because all the incoming edges to T, they are done. Now we are just worried about what lies ahead of T. So T is connected to U first of all. Let me just use here. So 2 plus 7 is 9. So obviously the previous value 6 will be retained. Then this one, 2 plus 4 is 6. It was infinity, now it changes to 6. 2 plus 2 is 4, and the distances are updated. So we move on to the next vertex. Now U is highlighted. U has a distance of 6. If you see, V had a distance of 6 also, but U 6 minus 1 from U to V changes it to 5. 6 plus 1 for W makes 7, but so we retain the 4. We just change the, okay. Then we move on to V. You see the distance of W is 4. V has a distance of 5. 5 minus 2 is 3, which is less than 4. And then the edges that are marked red, they show you the parent of the vertex. So when W had a distance of 4, its parent was T. That means you were traversing from source to T and T to W. But then when the distance of W got updated to 3, that was because of V. So now you are traveling from S to U, U to V, and V to W. And after W, there is nothing. So this is your single source shortest path for DAGs. Okay. So while you look at this and figure out, let me look for one good Bellman-Ford problem somewhere. I have it. If you have any questions, you can. Okay. So let me see. This is a graph, adjacency matrix given for a graph with 4 vertices. So 1 to 2, there is an edge. 1 to 1 to 3, there is an edge, and 1 to 4, there is an edge. Then 2 to 1, 2 to 3, and 2 to 4, 3 to 1. It's a two-way edge. 3 to 1 is 6, 3 to 2 is 13, 3 to 4 is 12, 4 to 1 is 8, 4 to 2. Okay, I'll take it back. Now here is again 8. 4 to 3 is 9. Okay, so this is your graph. I'm still drawing with my fingers, so it's not very tidy. So you have to apply Bellman-Ford. So what would you do? Let's put 0. Okay, so I'll just do a few rounds and you can continue. 1 to 2, you see that 10 is a smaller distance. So first time 1 to 4, 20, 1 to 3, 15, and that's it uh, for all the adjacent vertices of 1. Then 2 to 1 is 5, so 10 plus 5 is not a good value. 2 to 3 is 10 plus 9, 19. 15 is less than that. 2 to 4 is 10 plus 10, 20. So does no improvement. Then 3 to 2 is again obviously higher value. 3 to 1 again higher value. 3 to 4 again higher value. So these are the initial values you have to look for. You have to keep on relaxing 4 times. So we did once only. We did, yeah, we did only once. So we have to do it twice. For every edge, you have to do relax. And better if we can do this. Hmm. So actually, there are a lot of edges in this one too. 7, 8, 9, 10, 11, 12 edges. I'll give you another problem. I think this will not improve much in every relax. I'll give you a smaller problem so you can see uh, that how Bellman-Ford works. But one more thing, what I wanted you to see is in this slide here. Mm, negative. You can perform your Bellman-Ford on this one, okay, and take this just like an assignment to perform Bellman-Ford on this, and let's see if there is a cycle here somewhere. Um, there is a cycle 0, 3, 9, 11, 0. So if you see the weight of this cycle, it is 3 plus 6, 9 plus 2, 11 plus 3, 14. So the current cycle weight is 14. If you make two, once you're done with the Bellman-Ford for this graph, make these two weights negative. So your cycle weight will be 8 minus 6. The cycle weight is minus 2. So minus 2 means there's a negative 8 cycle. You will still be able to do Bellman-Ford, which you should do on this new graph with negative 8 edges. And once you find the final distances, so you know how many times you have to perform relax on this. And then once you find the final distances, if you perform one more relax, you'll see many of the distances will change because of the negative 8 cycle in the graph. And that is when your Bellman-Ford will return a false. Otherwise, before that, if when this was positive, it will return a true. It will return a true, and but your distances and your parents are updated, so that is taken care of. So if you see here, going back to here, so in this particular, they are not actually in this slide. You don't have actually have the relax function. So the relax function goes like this: relax of u, v, and w. So if dv is greater than du plus weight of uv, then dv is equal to du plus weight of uv, and parent of v is equal to u. Else nothing happens. This is you just when you're relaxing and you find a smaller distance, then your parent also gets updated. So this is your relax function. Okay. And similarly, what is your topological sort function? You say topological sort on a graph G is perform DFS on the graph, then insert the black nodes as soon as they are done at the beginning of the linked list, and that is your topological sort. So when you do it on paper, you also we put all the vertices in order and we draw the edges as given in the original graph. Okay, so you can try the example that for Bellman-Ford, if I find something which is a little bit smaller in terms of the number of edges in my handwritten notes, I'll send you a picture of that graph so you can try. So basically, I just want you can take any example online and try doing that as just like a homework, class homework. So I have also uploaded the tutorial sheets. That is also for practice. Your midterm is supposed to be online. It is supposed to be an MCQ type, but they won't be simple MCQs. The MCQs I'll ask you will involve some kind of calculations. So you will have to do some paperwork. Is your date sheet or anything out yet?
No, ma'am. No, ma'am.
They have given you first week of November.
Yes, ma'am.
Okay, that means next week. Yeah,
Yes, ma'am.
first is Sunday. So that means next week. Okay, then I have to start making the paper as well. So I hope, since it's an online exam, I hope all of you will study and do it on your own. Because I have some students who are BTech students living around, and I know what all they do to pass in their exams. So they're all prepared. Most of them, if they are locals, they all sit in one room, or they have one phone for online help, and they have another laptop for googling the answer. So you might score more, but it's better that you do things on your own. Honesty, like when my daughter writes her online exam, the last line, when they send the message, that's what they say: honesty. Please be honest in writing your papers. And I ensure that she does that. So I hope all of you also are honest when you're doing your papers. थोड़ा बहुत पूछना is okay, जब जैसे आप क्लास में दाएं बाएं देख रहे होते हो, बट ऑनलाइन में सारा and everybody will have the same answers, तो फिर वो तो खुद ही डाउट होगा ना. Then I can get the exam cancelled also if I feel like that. सबको सब मार्क्स मिल रहे हैं तो it becomes suspicious. Okay, so Uh, any questions on this? There are a couple of doubts people have asked. I will try to work on it and give you some notes. I'll also try and send you some example for Bellman-Ford and topological sort if I find one just now. I'll just check my notes and give you that. Okay. So, Aman, did you take the attendance?
Yes, ma'am.
All right. Okay. I think we are done. Thank you.
Thank you,
Thank you,
ma'am.
ma'am.
Lunch.